having seen the last session, I just raise questions. I will not try to give answers, so be a little patient with me. I just want to raise some questions, some very basic questions for us and possibly for others, or hopefully for others. And I want to question aspects of naturalism. That's my topic. And I do this the way that I have a very simple look on the basis of naturalism. Just looking on the definition, what is that, and what is the task they want to achieve. And then looking a little closer if this basement here is really solid enough to make a huge tower on top of that, or otherwise it might flip down. So let's have a quick look on the definitions. They're not so difficult, and I'm sure most of you, of course, know of these. Naturalism is the idea or belief, I find interesting here, that only natural laws and forces operate in the world. Okay, that's what we're talking about and how to deal with that, if this makes sense or not. And there's some extra stuff coming with it. And I have two of these here. And I find these very interesting. Non-physical substances, such as information, ideas, values, logic, mathematics, intellect, and other emergent phenomena can be reduced to a physical account. This is a very strong basis. I would say this is a courageous guy, and that's from him. He's a naturalist. So it's not us saying that, but that's what they want to achieve. And the other one, naturalism presumes that the physical world is orderly and comprehensible. By the way, this is something we also do. It's a very important assumption. And you see that I do a little red stuff in there, and that's the topics where I want to dig a little deeper. And by the way, when I dig a little deeper in this one, this is also a consequence for us here. It's a simple question: is the universe completely comprehensible? Would be nice, if so, but I'm not quite sure if it is. Now, in the definition we had previously, there was the reductionism part of it. So I also want to give a little information about this one. First of all, reductionism means that a system can be described in all its details based on its elements, their properties and relations. And again, we have lots of quantors in here in all its details. Once again, a very strong point we have, and three more. It must describe all cause-effect relationships, be expressible in effective mathematical models, and be consistent with experiments. So this one we had already, so I don't have to go into this one. I'd like to go into these two here. This is really standard definitions you find everywhere when you look in these topics. And again, this one I find very interesting. We're looking for mathematical models. We learned Thursday, without mathematics there is nothing. So we need these mathematical models. But the interesting part is this one. Why is this different? Why is mathematics and effective mathematics something different? There is mathematics which is not effective. We can describe things nicely, correctly, mathematically, but we cannot handle it because the mathematics is too complicated. Not so obvious, but this is the case. So where do we come from? So actually naturalism has a long history. There are lots of philosophers in here, but just to summarize this, we have Democritus, we have Epicure, and they came up with the idea that nature is just matter. Even the soul is a specific atom flowing in our whatsoever part of the body and generating the soul. And then came Newton, and he had this wonderful mathematics describing the universe, and then everybody was eager to completely describe everything. And we have this nice summarizing of this idea, and I would say that every naturalist would love this one here, to have it like this. So we take all the atoms, theoretically, and we know their location and momentum, and then we can calculate everything. Wouldn't this be wonderful? I'm not sure. At least this is what I guess that most naturalists would love to have. So this is a couple of time ago. Things changed a little bit in the meantime, so we no longer go like this, because when we dig a little deeper into physics, we realized that, of course, there's some part of physics where we can say, okay, we could principally generate Laplacian demon. So we have stable systems like a two-body system, a pendulum, classical mechanics. This behaves like this in principle, and this was just a principal idea. But then we found out that there are things like the weather, the double pendulum, which we cannot calculate. And this is a chaotic system which is not really stable, but we can predict it fairly long. So when you look nowadays on the weather forecast, and the weather forecast is for the afternoon, we are quite sure this is correct, and even if it's for 5 days nowadays, you get quite reliable results. This is what typically is called long-term predictability. And then there are things which are even worse than that. We have multiple objects, bodies, and how they interact. So the 3n body problem is completely chaotic. So this so quickly can go away, and we have no idea what happens. And worst case is quantum mechanics. This is just noise. So looking on a single atom, we have no idea what's going on there. So the demon has gone. So he's living in a very small portion of reality. Otherwise, all interesting parts of physics cannot be calculated. So we squeeze down this idea a little bit. But still, here I have a citation from a German physicist. He says that the standard model, so he's referring now to elementary particles, the standard model is far more than a theoretical model of elementary particles and their interactions. It claims the rank of a complete theory of all observable phenomena of elementary particles. For the specialist, this theory can be written within a few lines, and it forms a kind of world formula. Wow. We are close. Naturalist is winning. We have it. We have the world formula. But this is a famous guy, and this is what, when you go to the internet, you find quite on top when you look for these topics. So, and when you look into the newspaper, into reports about results of nature, this is how our journalists like to present results of nature, of science or nature to us, like this. We are very close. We have more or less the world formula. Let's take a very simple example and check if it's really a world formula. What we do is, let me just summarize this. Originally we had the Laplacian demon, but we skip the prediction. So naturalism goes a little down. So what remains is that we make a description based on the laws which is complete and effective. This is now the status naturalism wants to reach, complete and effective. And I mainly go for this topic here. And now let's test this on a very basic thing. We just read that we have a world formula for elementary particles. So we can derive from this the behavior of atoms, and from this we can the behavior of molecules. What you realize is actually we cannot do that. Knowing all features of an atom or a molecule, we have no idea how the solid part, the liquid part, or the gas part will behave. There's no way going from this perfect explanation of a system to the next level. It's amazing. A world formula which cannot go much further from elementary particles up to the atoms. Correct me, there are some physicists in here. What I learned is that what you do is you check, let's say, for example, atoms, and you check if this observation you have is compliant with the underlying theory. You do not derive from the theory up to the atoms, not from the atoms to the molecules, not from the molecules to liquids or whatsoever. You do this within levels. So what we find is a description like this. The reality is hierarchically organized in an increasing complex systems, whereby each level is in first approximation independent of the lower level. For each level, there are new laws, new terms, new methods, and approximation necessary. Again, a standard definition. This is a very neutral part of science we are talking about here. And in a way, we are lucky because we are still outside of biology. So this is a safe ground, and we can easily discuss with everybody. So, but when we look a little closer, this completely contradicts what we had as prerequisite for naturalism. To repeat that, non-physical substances such as information, ideas, values, logic, mathematics, intellect, and others, emergent phenomena can be reduced to a physical account. And looking into reality, we see, no, sorry, we cannot do that. Whenever we go one level up, we miss everything which is below, and we start again. We make physics for atoms, we make physics for molecules. So talking to your biologists, try to get an idea if you have some molecule, how and if it will interact with another molecule. You just try, don't you? Because there's no general understanding of how every molecule would interact with each other. It's not there. So what I see is the following. The thing we understand from nature is like in kind of levels. Let's say we have elementary particles, we have atoms, we have molecules, and we have a fairly good understanding of these levels here. Really nice. And even think of the boson. We had this perfect prediction that there must be a boson, and a couple of years later, they found it. So within these levels, you have full power of mathematics, and people wonder how can it actually work so well? But then we want to go up to the next level from elementary particles to atoms. Prediction is fairly hard here suddenly. And even understanding the atoms, we cannot predict all elementary particles below that. We have to do experiments on this level again. You cannot just predict from here to here. And even worse, there's some mystery in here, which is called emergence. So here's something, and then we go up. So, and this is a phenomenon which is actually not normal in our world. So take Lego pieces, and you have a single Lego piece, let's say that's an elementary particle, and then you give this to a child and it builds a house, and it's still a couple of Lego pieces. But here we have elementary particles and go to atoms, and they are completely different. And if you ask a physicist, it says, this is emergence. How does it work? This is emergence. This is why I have this magic wand here. So the real leg going from one level to the other. So why do we not have enough information here to go up? Why is there not information to predict? Why can we not go down? So from my point of view as a computer scientist, I would expect that this is a more smooth transition here. What happens, specifically because the complexity is going up significantly. The number of laws goes up. By the way, the number of laws we're using here, we ignore completely up here, more or less. So there comes new laws and we forget about the others, unless we do something which refers to this level. And at the same time, we have the laws of thermodynamics. They would tell us everything wants to go down here, but actually nature loves to increase complexity for whatever reason. We do not know why. Okay, so you get the feeling where I want to go to, and hopefully you can follow me now with a more quick digging deep into different parts of computer science and logic. Let's take the following idea. We have nature, the complete universe, and there's some divine being, and it tells us all laws with which you can describe nature. We don't have all these laws, but let's assume we have them for some reason. And the question would be, how complex is this mathematical system we get? I think you have to digest this idea, because typically you don't think this way. What we normally do, we have a problem, we describe something new. We have another problem, we describe something new. Now let's assume we are ready, we are done. And the question I'm raising is, what is the complexity of this mathematical thing we get? And then the second question is, what is the outermost complexity we can handle as humans? Very basic questions. Having two numbers here, or two kinds of descriptions, and we look deeper into that one a little later, the question is this inside or outside? Is the complexity of the university inside our capabilities or above? Very simple question. Now, how to handle that? And in mathematics, we have some tools of handling complexity. And I want to give you a first idea how this can be done. And the idea is the following. We take the natural numbers. Natural numbers are somewhat easy. Kids start in first class or kindergarten to handle that, so it should not be so difficult. And we describe complexity by subdividing all natural numbers in subsets. Some are very easy, like all natural numbers is a subset of all natural numbers. That's an easy set. We just count 1, 2, 3, 4, 5. Now let's say we take every second one. So we take all even or odd numbers. A little more complicated, but still feasible. We take all prime numbers whatsoever. So we subdivide this whole set of all integers into more and more complex parts. And this is what this hierarchy represents. So instead of saying we do this by looking on the numbers, you could also say by the description. So the more complex the mathematics we use, the more complex will be the outcome. And this is what this implies. This is the number of quantifiers we use here. This represents existence quantifiers, and this represents universal quantifiers. So more and more complex formulas, and with this increased complexity of these formulas, the sets we can describe are getting more and more sophisticated. So this is an infinite hierarchy. Will never end because we can add more and more quantifiers. The very lower part, this is already a huge set. This is everything we can compute with a computer. And that's a huge number of sets. Of course, even and odd and prime numbers, this is everything we can calculate. This is a little more difficult one. This is a part of sets where there might be an answer in case we start the computer. There could be the answer yes, and then at some time it stops and tells us yes, or it might never stop. But we don't, at no point we know if it ever will stop. So we have to wait and wait and wait. Like you have an appointment for a restaurant and you're waiting. Hopefully your wife is coming. You never know if she really comes when she's there. You're lucky. If not, you have some argument at home later on. This is this more complex part we have here. So this we can deal with completely, and this we can deal with partially. This is called computably enumerable. So things we can give more and more of, but we cannot get everything at the same time. So you guess this is a fairly huge amount of space we have. And to come back to my question, where's the universe? So the description of the universe is in here, or here, or here, or here. We do not know. Some facts on nature. Somehow proven. We are on the vague area now. There's a strong assumption that there are uncountably infinite physical events in the universe. Uncountable means it has the same complexity like the real numbers. So the uncountably is outside of integers. So this is a fairly complex thing. The problem is that it's an infinity we cannot even deal with. And just to mention two guys, what they conclude from that, this comment, there are more facts in nature than truths. Truth means I can prove something to be true. This is the sense that I can make a statement about that. So I can make less statements than I can observe. And the other one is that there's an ultimate non-scientific limitation of science abilities. Okay, digesting that. Let's look on that topic from another side. That's computability. We already heard that this lower set we can compute, which means there are other tasks we cannot compute. And here's just a list to give you an idea of things we know we cannot compute them. And computing means you have a program which is designed to solve a task, and you give some input and ask, is it true or not? Various things in logic, abstract machines, matrices, and so on. So this is also an unsolvable problem. Sounds very easy. You get tiles. So you have got for shopping, and she wants you to tile the bathroom, and she has some strange shapes, and she asks, can you put this on the floor that there are no gaps in between the tiles? This is a problem which is not decidable. There's no computer given any kind of tile to solve this problem. Of course, if they're all squares, this is somehow easy, but for an arbitrary shape, this is not decidable. Or even worse, there's a famous theorem from Rice. He states that every interesting property of programs are not computable. There's no program which can give you the information if this program will ever return 0. If two programs have the same results whatsoever, all these basic semantic things you cannot get out of a computer. So we have some limitation. To you, this might sound a little artificial, but now digging a little bit into physics, there are two parts, at least two I know of, which are not computable. The Hamiltonian mechanics is not decidable. Well, the equations do not look so nice for some of you. You have to do some differential equations here. But from the theoretical point of view, this is not decidable. Also, group theory is not decidable. Group theory is something physicists like in the field of atomic physics. Because with these state machines you have, like the spin, in two positions can be rotated like this and like this, is quite often modeled with group theory. And there are various problems in group theory which are not decidable. Here's one example of those undecidable problems. So we go a little into reality. That is, we have parts describing nature, knowing that they are not decidable. You see, this is undecidable. I would agree on that. Okay, a little more facts. Might be a little strange thought for you, so let me help you to get this one. Think of the whole universe as a computer. So you put something in and it behaves in a given manner, following the laws, and it yields some output. And there are three assumptions currently how the universe is equivalent to some theoretic machine. The first idea is that the university corresponds to so-called Turing machine. You can consider this as an ideal computer, meaning it's always working, has infinite memory and everything, so perfect computer. Now let's assume that this is true. Then we could use our computers, and on the other hand, the world would be equivalent to a computer program. But unfortunately, because computers are not decidable, all the real questions on the university on the universe cannot be answered. Because every serious question, as we saw from Rice's theorem, are undecidable. Every real semantic question on arbitrary programs are not decidable. which means every serious question on the universe are not decidable. Oh, okay. Let me jump to this one. There's a hypothesis that the universe is even more powerful than a standard computer, a so-called hypercomputer. And we would be able to build a hypercomputer, which is way, way faster. Still, we run into the same system because then the universe would be more complex, but at the same time, the questions would be more complex. So it doesn't change anything on our way of understanding the universe itself. Coming from the logic side, we learned from Gödel that pure mathematics, so the formal part of mathematics, is limited. And we cannot even describe natural numbers in a way to handle it completely, to say that much at this point. And the problem behind that is that once a system is getting too complex, we cannot handle it anymore. If it's too weak, it doesn't express what we want to do. So people in logic try to find a level in between being strong enough and still being able to handle that. So if this machine is getting too strong, the boy cannot handle it. That's my idea behind that one. And unfortunately, there's no line in between that. We have to do it that powerful, and then we cannot handle it anymore. So in logic, we reach the point, if we describe serious systems, we cannot handle these systems anymore. And there's no way out of that. And the nice part is, logic is a real proof with a universal quantifier in front of it. Another idea, to give you a thought that this is very basic thing here. Whenever a system has a given complexity, this system is no longer able to talk about itself. Like we have the piano axioms, you cannot talk about these within the system, so you need a stronger system. So a human can never understand itself completely. So by principle, actually, we cannot understand the universe completely because we are part of the system itself. Because we have reached a complexity where the system cannot argue about itself anymore unless it's trivial questions. So to me, it looks like this. I'm not sure if some of you like Asterix. It's the story where Gaius Bonus, a high-ranked soldier, convinced the others to make a magic potion for him. And so this is, we are now with Laplacian again. Laplace got his idea, and now he starts, and he thought he has the magic power, and he tries to lift, and this is too big, and this is too big, and this is too big, and at the end he finds a small one and says, I'm a Superman. And he says, what a kind of miracle. So it feels to me that naturalists get used to all the limitations they have, and they are satisfied with all the reductions they get step by step, and still they say, I'm a Superman at the end. But it's actually not working so well. I'm coming to the end. There are two ways of thinking about the outcome of that. And these are two, I mentioned Gödel already posted, another one of the guys who were highly involved in looking into these details. He says that these results I have presented are a fundamental discovery in the limitations of the mathematization, wonderful word here, power of the Homo sapiens. So this is serious limit. Gödel has another position. He says the results we found are on a theoretic level. So it limits logic, but it doesn't limit our mind, because we think on a semantic level, so we are not in that one. So Gödel in a way says we skip this portion here. We don't longer go into effective mathematics. It's too difficult, we forget about that, we discuss about it. So whatever we choose, well, if this one, then the story's over. So let's go with Gödel. And actually it's the way that humans can prove things where formal logic can no longer get a result by being smart in a way. This is very interesting to see. And this idea inspired computer scientists to say, what kind of complexity actually can humans solve? How complex can problems be so that we can deal with them? And coming back to our hierarchy, the current hypothesis is that humans can go up to this complexity of problems. Remember, this is the ones we can solve with computers. So we are 2 levels up. Very interesting. Now, but concerning naturalism, there's a little problem with that. This should not exist in our universe, because we are part of this universe and we follow the rules of the universe. So how could we solve these problems being part of the universe? So this is a strong contradiction. So we can do better than we should do. So whatever path we follow, if we follow Post, we have to stop. If we follow Gödel, we say, oh wow, we can do great things, but this should not be the case. Because on a naturalistic basis, we cannot explain this anymore. Okay, and not to go into detail, I have raised a couple of questions, and for me this is a kind of list, things I want to look a little deeper into. Are they really provable things we cannot compute, cannot prove, cannot even model, or cannot even perceive? So the more complex systems are getting, there might be the chance that we even cannot perceive them. And then, of course, what kind of conclusions do we follow from these intermediate results? This is, of course, getting stronger and stronger down here. So I'm a little over time, I'm afraid, but thank you very much. And a little citation from Goethe. Sorry, I don't have an English version of that, but I think it nicely summarizes what I have in mind here. Thank you very much.